Hello, my name is Eric Sollenberger, and I'm going to be giving a demonstration of the proof of concept system for the Spectrum Management Research Testbed Self-Sustaining Broadband Network, or SMART SSBN. Here we have a block diagram of the proof of concept system. The hardware was selected so as to meet the basic functional requirements described in SMART SSBN's proposal. The first of these requirements is to extend broadband service to remote locations. This is accomplished by using two wireless routers. The first router is an access point for users in the remote location. The second router provides a backhaul link to the internet by operating as a client in another Wi-Fi network. The addition of a directional antenna will extend the range of this connection into areas where this network was not otherwise available. There are also two USRPs, one of which can be used for cognitive radio and spectrum sharing experimentation, while the other can be used to monitor the spectrum. A single computer acts as a server for both USRPs. Each of these devices can be accessed remotely from the internet. This proof of concept system can easily be made mobile since there are no wired connections leaving SMART SSBN, and all of the hardware is relatively small. Here is a photo of the hardware just described set up. This first demonstration will show that broadband service has been extended out to users in SMART SSBN's Wi-Fi cell, and it will also show how one of the USRPs can be used to monitor the spectrum's usage. First, I'm going to remotely access SMART SSBN's internal computer. In this demonstration, I'm actually on the same local area network as SMART SSBN, but these same ports can be accessed from the wide area network as well. Now that I've logged in, I will run a GNU Radio Python script, which will allow us to observe the spectrum that SMART SSBN's Wi-Fi cell currently occupies, and to estimate the channel usage. Here's an FFT of the Wi-Fi channel. The center frequency is set to 2.432 GHz, SMART SSBN's channel. We can also see that the measured channel usage is very low, around a few percent. Now we will see what happens when we actually use the link. I am now on a separate computer whose wireless configuration shows that it is indeed connected to SMART SSBN's Wi-Fi cell, and that the channel it is using is 2.432 GHz that we tuned to before. So now I'm going to start streaming an HD YouTube video, and we can observe what will happen in the Wi-Fi channel. Now that we are using the Wi-Fi connection, we can see the carrier pop up in the FFT a lot more. Also, when we look to the channel usage measurement, we see that it has significantly increased, going from a few percent to roughly 25%. The ability to measure channel occupancy in a manner similar to what was just shown would be critical for spectrum sharing experimentation. This demonstration will show how SMART SSBN might be used for cognitive radio and/or spectrum sharing experimentation. It will use a modified version of a software package that has been developed at Virginia Tech called Cognitive Radio Test System, or CRTS. One of the USRPs of SMART SSBN will be used as a cognitive radio test node. The other will be used to observe the spectrum. An additional external USRP will be used as a second cognitive radio test node with which SMART SSBNs will communicate. I am starting two remote sessions from my personal computer on Virginia Tech's Wi-Fi network. One is with SMART SSBN's computer, and the other is with a separate computer that is on the same local network as SMART SSBN. First, I will launch a GNU Radio script to view an FFT of a 5 MHz wide channel centered at 460 MHz using one of SMART SSBN's USRPs. This will allow us to observe the interaction of the two cognitive radios. Next, I will run CRTS on the two cognitive radio nodes. To review, this is the relation of the hardware to the windows displayed on the screen. While CRTS runs, we can observe metrics of the radio link being printed to the screen for each packet that is sent between the two cognitive radio nodes. These metrics can be set to include error vector magnitude, received signal strength, and bit error rate, among others. We can also observe OFDM carriers occasionally in the FFT at 458.5 and 461.5 megahertz. Finally, once the first testing scenario is complete, summary metrics are printed out to quantify the cognitive radio's overall performance. In this way, the proof of concept system for Smart SSBN demonstrates its ability to test cognitive radios, and with some additional code development, it will be able to incorporate spectrum sharing experimentation as well.